in order to calculate it, I need to know what is the mean of this distribution, what is the mean of this distribution, and what is the width. Can you say, okay, so what is the mean of this distribution? Let's call it mu1. What does that mean? What is mu1? What is mu1?
It's the weighted sum of the averages of the neurons.
This is L. We need the mean of this thing given that theta is theta 1. So what is that? Some W. Yeah, we need to take the means of Ri given F1, which is very minus. So this is sum of Ri, Wi, Fi minus. And likewise, mu2 is sum over I, Wi, Fi plus. We also need the standard deviation. Is there anything that you can tell me immediately about sigma 1 and sigma 2?
Would be the same.
Yeah, they will be the same. Why will they be the same? Because these two distributions have different means, but once I subtract the mean, everything that I get is from the noise, and as we discussed, the noise has the same distribution regardless of theta. That was our assumption. This, because of Cij, is independent of theta. So sigma 1 is equal to sigma 2, and let me just call that sigma, and I just need to calculate it. Right? So we wrote already what is mu1, what is mu2. Obviously, as we discussed, the optimal decision point will be just the mean of them. And what will matter for the error is the ratio between sigma and the difference between these two values. That's all that matters. What determines this area is, again, the ratio between sigma and the distance between these 2 points. Okay, so let's calculate sigma.
Can you explain again why the ratio is the same?
Well, first of all, clearly, if I would move around these plots, if I would change mu1 and mu2, if I would add something constant to mu1 and mu2, this would not change, and to keep sigma fixed, this would not change the area under this. If I would shift all this plot to the right or to the left, it does not change this area. What do I need to calculate? I need to calculate this area. I need to calculate the area behind below a Gaussian that starts at this point. What is this point? It's mu1 plus mu2 over 2. And so let's just shift this whole graph such that mu1 will be at 0. Then now it's a Gaussian centered around 0, and I need to calculate the tail of that Gaussian beyond the point, which is mu1 plus mu2 over 2. Sorry, which is
Mu over 2.
yeah, it's now mu. Yeah. Okay, we'll do it later. You know what? We'll just do it mathematically in detail a bit later. Okay? So you will see.
So just what you said, what determines the error?
But my argument, the way to think about it, I will answer your question in a moment. The way to think about it, another way to think about it is just to think about units. I mean, what? How should I say it? If suppose that the RIs had some units, then L would have, and W is dimensionless, and L would have these units. We have to generate something which does not have dimensions. So I mean, it's clearly the difference between mu2 and mu1 that matters, and not their absolute values, because of what I said, that if I shift this plot, if I add something both to mu1 and mu2, it will not change this area, right? So it's clearly the difference between them. And I claim that it's also not just the difference, it's the ratio between the width of these Gaussians and this difference that matters.
You're saying it's equal or proportional to the ratio?
No, it's not equal to the ratio, it just depends on that ratio. It can have, as you will see, it has a complicated dependence on that ratio, but it depends only on that ratio. If I would, another way to say it is if I multiply sigma by a factor and multiply this difference by a factor, then the area under this will not change. And you will see it in detail. If you don't believe it, you will see it in detail. So for now, what I want to do is to calculate sigma. And so let me write sigma squared, the variance of this distribution. So I can write it as follows. I take the response, I subtract the mean response. I take the L, okay, this is L. I subtract the mean of L, which is sum over I, Wi, Fi of theta. I square this. And this, by definition, is the variance, right? Which theta? Okay, what am I averaging over? I'm averaging over the distributions of the responses given theta. Which theta? Doesn't matter. This will be the same regardless of theta, and we're interested specifically in theta 1 and theta 2, and this will give us sigma 1 and sigma 2, which are the same. Okay, so let me write this a little bit differently. And I will write this as sum over I, Wi, Ri minus Fi, and I will write the squared sum as a sum over I multiplied by sum over j. So I'm doing it a bit with skipping some steps. I will write this as sum over I and j, Wi, Wj, Ri minus Fi, Rj minus Fj. And now I need to take the average. So this is just what is inside this average. I need to take the average. The average is over the distribution of R. Wi from our point of view are now fixed. So nothing to average. I can put on. I can put the average. I can take this out of the average, the Wi, Wj. So I can write the average only on these terms. Okay. Now, what is that? Yeah, that's the covariance matrix of the noise. And by definition, by the way we constructed it, this is Cij. So, what we have here is sum over I and j, Wi, Wj, Cij. And now let's write the probability of error. So I will write down the probability of error under the assumption that theta is theta 1. But you can convince yourself easily in a moment later that it's also the probability of error if theta is equal to theta 2. So I should have written pre-error is half times the first one and plus half times the second one, but they're equal to each other, so I can just write one. So I need to calculate this area. What is that? So we have a Gaussian. We need to take the Gaussian, integral of the Gaussian from this point to infinity. So this point is mu1 plus mu2 over 2. And now I need to write down the normal distribution, which is 1 over square root 2 pi sigma squared, exponent of minus x minus mu 1 squared, because we're dealing now with the response given theta 1, so its mean is mu 1, divided by 2 sigma squared dx. And you know what, I was planning initially to just skip some points, but maybe just to clarify why I said earlier that this depends only on the ratio between sigma and mu1 plus and mu2 minus mu1. We can define a variable, let's call it u, which will be x minus mu1 divided by sigma. Okay? So du is dx over sigma, right? And when x is mu1 plus mu2 over 2, then u is mu2 minus mu1 over 2, right? Do you agree? When I plug in x mu1 plus mu2 over 2, divided by 2 sigma. Okay? And so this is an integral going from mu2 minus mu1 over 2 sigma. This is this lower bound. And when x is infinity, u is also infinity, so the upper bound remains infinity. Now, dx, as I wrote now, is sigma du. So dx over sigma, which we have here, we have dx over sigma, is just du. So I can write here du divided by square root of 2 pi. And now here we'll have x of minus u squared over 2. Right? So everything here now does not involve any parameters. The only parameter that remains is this.
Is it r like here? R squared?
What?
What is in the exponent in the...
Here, u squared.
U.
So I just rewrote it as in terms of this variable, and no parameters here remain. So the only parameters in this integral is this one, and you can see explicitly that it depends on the ratio of mu2 minus mu1 and sigma. Okay. And furthermore, this is nothing but a complementary error function up to the the definitions, the prefactors of how it's defined, which I never remember, so I always look it up. And this is half the complementary error function of, I will write it as follows, d prime over 2 square root of 2, where d prime, just to conform with the conventional definition of discriminability, which we discussed already. So d prime square, by definition, is mu2 minus mu1 squared divided by 2 sigma squared. Sorry, without the 2. Okay, so it's just a way to write it as a function of this quantity. Okay, but now I can plug in this expression what I know is mu2, what is mu1, and what is sigma. So first of all, in order to have a small likelihood of error, for the probability of error to be small, we want d prime to be large, right? We want the ratio between these means to be large compared to the width of these Gaussians. And now we just need to ask ourselves, I should plug in here what is mu2, mu1, and sigma as a function of w. and ask myself what is the best choice of W such that this prime will be as large as possible. So let's do it here. So d prime squared let me add another definition here. So you see that everything will depend. So mu2 minus mu1 is sum wi fi plus minus fi minus. So it all depends only on the difference between, it doesn't matter what is the absolute response of the neurons to theta 1 and theta 2, it matters what is the difference between the responses to theta 1 and theta 2. So it's convenient just to define gi as fi plus minus fi minus. And in terms of gi, what we have is then sum over I wi gi squared divided by sum over I and j wi wj cij. And in the vector notation, vector and matrix notation, I can write it as G transpose W squared divided by W transpose C W. Okay, so this now is a function, the probability of error is now a function of the choice of the weights, and I want to find the weights that will minimize the probability of error. So I need to take a derivative. To find the optimal weights, I need to find weights such that the derivative of this quantity with respect to W is 0. So so optimal weights. We need to solve the set of equations d prime squared to dwi equals to 0 for all I. So so in general, what? Oh? Okay. So in general, one thing which is a useful thing to remember whenever you have to deal with an optimization of something which is a ratio of two things is that if you want to require that if you have something which is a ratio of two things, as we have here, and we're looking for the derivative of this with respect to some parameter x, and we want that to be 0,